Hello everybody, and welcome to our webinar. My name is Vladimir Podnos. I am Director of Marketing and Support of Terra Analysis, and today, together with my colleague support engineer Alex Lubimtsev, we will tell you about possibilities to expand the core functionality of QuickField with programming. QuickField is extremely simple finite element environment, allowing simulating of the wide range of tasks: electromagnetic, heat transfer, and stress, practically without training. QuickField workflow is very straightforward. You need to define the model geometry, you need to define material properties, boundary conditions, and then you click button to generate the automatic mesh, then you click button to solve the problem, and then you may enjoy analyzing the field using the color maps, plots. You may create integrals, see local values. It's very easy and straightforward and nothing to worry about. But sometimes you need not just one simulation. We also provide simple utilities for more complicated analysis. For example, there is a parametric tool called Label Mover, which allows you to simulate and modify QuickField model geometry or physical parameters and perform serial analysis, tolerance analysis, solve tasks of optimization, and parameter identification. But there may be situations where our core functionality of QuickField as it is, extended by family of tools we provide, may not be enough as well. For example, you may want to combine QuickField simulation with real-time information provided by sensors, thus allowing monitoring of the internal temperature of some object. The direct measurement is impossible, and you need to solve heat transfer problem with boundary conditions adjusted based on the sensor data. This task requires programming. Or you want to include a finite element model as a part of automatic control system. In this case, QuickField simulation will dynamically obtain dynamically changing initial data and boundary conditions and provide the control unit with necessary results in real time. This task also requires programming. And there is plenty of situations when the simulation should involve not only electromagnetic but other physical processes not covered by QuickField functionality. For example, it may be dynamical and kinematic calculations based on the electromagnetic forces, and results new position of the object also affect the fields, thus the forces, and iterative process is needed. Today we will show you in details how to bundle our finite element model with external models, which implement needed additional functionality. We will cover only this particular application, but you should understand that the approaches and methods are the same. Today's programming is usually performed in one of integrated programming environments. There are plenty on the market today. Choice is individual, and many engineers prefer using not dedicated programming system, but engineering or business environment, not specifically meant as a programming environment. You may develop additional tools interacting with QuickField in Visual Studio, MATLAB. You may program Excel macros using Microsoft Office Visual Basic for applications. You may use Tcl scripting language. You may use VBScript. Choice is wide, and you may find the system where you are most comfortable and you may use it. But today we will mostly speak about using Excel with macros written with Visual Basic for application. Again, it is very simple tool, QuickField, and programming with it is also relatively simple, and Alex will show you how to do it in real time using real QuickField running in background. It's not a static set of presentations, it is real QuickField in real situation. Thank you. Alex, please.
Hello, my name is Alex. I work in QuickField support team, and today I will show you how to use dynamic characteristic of the electromagnetic relay. On your screen you can see the electromagnetic relay. The relay consists of the following parts. There is a winding, a coil. There is a steel plunger. There is a damper, the spring that keeps the plunger in the extended position. And the task is to find the time required to pull in the plunger. Relay operation is very simple. After the current is switched on in the winding, the plunger is pulled inside and the contacts are disconnected. You can see the relay data. We know the plunger weight, the extended and pull-in position. We know the spring strength, the spring length, and number of turns and the current. The process can be represented by the mathematical model. These are the equations. F is a total force acting on the plunger. M is the mass of the plunger. A is acceleration. V is a speed of the plunger. Delta T is an integration time step. And X is a plunger position. Solving these equations, we can find the X position and the speed as a function of time. Why we need QuickField here? That's because the force depends on the plunger position. It consists of the spring force and the magnetic force. And for each position, we have to simulate magnetic problem to find the magnetic force. But why we need programming here? Because the field simulation is not enough. We need to simulate the plunger movement kinematics outside of QuickField and link this with field model. The program algorithm is very simple. First, we should read the initial data, relay data, plunger position, initial speed, weight, spring force. Then, for each position of the plunger, we should run QuickField and calculate electromagnetic force. Then, here, we should add the spring force and calculate acceleration, speed, and new plunger position. And with new plunger position, again, we go to the beginning and calculate electromagnetic force, and the cycle runs again. The process stops after the plunger gets into the final position and hits the stop ring. Let's start QuickField and take a look at the problem. This is my relay simulation problem. The problem type is magnetostatic. The problem class is axisymmetric. This means that the axis of rotation is a horizontal one. In the model, I have the winding with the current specified. I have the plunger. The plunger consists of the steel core and the cover. For the steel core, I specify the permeability, or it could be a nonlinear problem. But this is the case study, so it's a simple linear problem. Now let's run the simulation. You can see the field lines. Let's calculate the force. To calculate the force, I should select the plunger. Then I open the integral calculator and select the mechanical force in the integrals list. So this is the mechanical force acting on the plunger, and you can see the direction is on the left. The plunger is pulled in the coil. To find the force at another plunger position, we should move the plunger in the model, run the simulation again, and calculate the force. Now I operated QuickField using graphical user interface, but exactly the same could be done using application programming interface. As a programming tool, I will use Microsoft Excel, or more specifically the integrated Visual Basic for applications development environment. Let's start the Excel. Here you can see the relay data are stored in the Excel sheet. These are the equations, just to remember them. The calculation results will be stored in the table and shown on the plot. Now let's start Visual Basic Editor and take a look at the program that is hidden behind this Start button. Here is the Visual Basic Editor and my program. The program is very simple. It has the same blocks I showed on the diagram. Here is the test block, the initial data are read from the Excel sheet. I need the initial speed, initial plunger position, final plunger position. I read the plunger weight, the spring strength, and the spring length. All this data I take from the Excel sheet. The next block is integration parameters. I have the integration time, I have the time step, the step counter, the force, and the acceleration. And the next block is our solving algorithm. It's very short and very simple. First, we calculate the force in QuickField. Then, to the electromagnetic force, we add the spring force. Then we calculate acceleration. Then we calculate the speed. The speed that gains the plunger during the small time period. Then we calculate new X position of the plunger. Time, counter, and output parameters are stored in the Excel sheet. And that's all. There is no QuickField used yet. Interaction with QuickField takes place in this getForceX function. The function takes X position of the plunger as an input parameter and returns the force. Let's take a look inside this function. Here it is. Here is the function that describes interaction of QuickField with our program. In Visual Basic, if you plan to use external application object model, you should first place the link to this object model. This is the link to QuickField object library. So now I can use QuickField objects in my program. These first strings is hello world. We set the link to QuickField application. If QuickField is not running yet, it will be started. Then all the actions I did to solve the problem are repeated. I take the problem, I load the model, I check the plunger position and move the plunger to the desired position. Then I build the mesh in the model. I save the model. Then the problem is solved. Then I open the results. Then in the field window, I build the integration contour to calculate force. Then the force is calculated. and the force is returned as the function result back to my program. Let's run this program. I will run it in step-by-step mode and show you how QuickField responds to all the actions. Now you can see both the program and QuickField. And we start. The initial speed 0. The initial position, I take it from Excel. 10 millimeters. The final position, I will take it from Excel, is 6 millimeters. The plunger weight, the spring strain, the spring length, these are the data specified here in my Excel sheet, so I just read them from my Excel. Now I should specify integration parameters. Initial time, integration time step, counter. I use the counter to prevent the program from infinite loop. If the force is low, the plunger may be not moving at all, and the program stops after 20 steps. Now this is the solving block. Let's run it. The force will be calculated with QuickField. Now this is the part of my program that interacts with QuickField. I set the link to QuickField. I set the link to the problem. I load the model. I will close now the model to show you how it happens. The model is loaded. I check the plunger position. I have the special node here to check the plunger position in my program. So I check the X position of this point and compare it with the X position I take as an input parameter and decide if I have to move the plunger or not. So for this vertex, I take X position, this is the desired position and this is actual position, so I have to move my plunger. And in this string, I will move the plunger. You see the plunger was moved in the initial position 10 millimeters from the beginning. Now I have to build the mesh. I have to save the model. And I have to solve the problem. Now I need to analyze the result. I put the link to the result. In the field window, I have to build the contour. I will add the plunger core and the plunger cover to the integration contour. And now I can calculate the force. It's nothing, but now here is the force. Let's take a look at QuickField and compare. Is it a correct number or not? Very well, it's the same number. Now I can continue with my program. I know the electromagnetic force acting on the plunger. Now I add the spring force, and the total force will be this value. I divide the force by the plunger mass and find the acceleration. I know the acceleration, and in a short period of time the speed will change from 0 to this value. I know the speed, and I can find the next X position. It was 10 millimeters, and now it is 9.87 millimeters. Next step, counter, and save all the data in the Excel. This is Excel, and how I save my data there. Counter, first step, time, X position, speed. And we can continue again. I will run the program now without breakpoints, so you can see how it works dynamically. The plunger is moving and the data are stored in Excel. These are the data. The plunger hits final position, 6 millimeters. And you can see on the plot how the X position and speed changed in time. It required only 45 milliseconds to hit the final position. With this program, you can easily change the relay data and run the simulation again. For example, if I set the stronger spring, 5 instead of 4, and run the simulation. It will take longer to hit the final position. In this example, I'll show you how to use QuickField from ActiveField or using QuickField programming interface. But QuickField programming interface or QuickField object model is not the only way to interact with QuickField. QuickField features full-blown application programming interface. We use this interface ourselves to create add-ins to QuickField. These are capacitance matrix calculator, label mover, and many others. Some of these add-ins has their own programming interface, and I will show you the parametric tool label mover and a parametric programming interface. First, I would like briefly to explain what the label mover is. Label mover is a tool used to automate serial calculations, to perform tolerance analysis, and for optimization. For example, with label mover, I can easily find the force as a function of plunger position. Let me show you. In label mover, I choose the base problem. That is the same relay simulation with QuickField. Then I choose what value to measure. I will measure electromagnetic force acting on the plunger. Now I will add the value. This is the value I will measure, the force acting on the plunger. Then I specify steps. I will move the plunger in X direction by half millimeter. And I will repeat this step 8 times. Now everything is ready. I can run simulations in unattended mode. I press Get Result button. You can see the series of problems is generated. Then in each problem the plunger is moved to a specific position. The problem is solved and the force is calculated and stored in the table. QuickField in this mode is controlled by the label mover. And now I can see the result, how the mechanical force depends on the plunger position. This is the label mover add-in and it's used for the serial calculation. Now back to programming. Label mover has its own programming interface. To program with label mover, you should switch it in optimization mode. Let's start from the beginning. I will open a relay problem. I will start label mover. I will switch label mover to optimization mode and will choose the base problem. Now remember that to calculate the relay dynamics we need to move the plunger and calculate the force for each position. So I have to add the values to measure. The mechanical force, and I should specify the variations. I know that I can move the plunger from 6 to 10 millimeters. Now I can save the label mover script and open the Excel document. It's the same program here. Let's open the VBA editor. Now you can see the program. This is the initialization block where I read data from Excel. This is the time integration parameters block. And this is the solving block. It's the same as in the previous program. The only part which was changed is the get force x function. Now the function is very small. All actions are translated through label mover. The link to label mover is added in the reference list. Now how it works. We tell, first we set the link to label mover, then we tell label mover to make one step with specific parameter. The step itself is described in label mover. It's a standard part of label mover functionality, and no extra programming is required. Then we tell label mover to simulate the problem and to return the first result. The result calculation is also the part of label mover functionality. No programming is needed here as well, so our program is very short. Now let's run it and see how it works. I read initial data from Excel. I will show you Excel. The spring strength, the spring length. Now I specify the integration parameters, the integration time, the time step, the counter, the force and the acceleration. And this is the solving block. First we get the force from QuickField, actually not from QuickField but from label mover. I set the link to label mover. Then I ask label mover to perform the variation, this variation. Move plunger to specific position. Then I ask label mover to solve the problem. The problem was solved. And then I ask label mover to return the result. And the result value is the mechanical force for the plunger. And that's all. Then I add the spring strength to electromagnetic force. Then using this total force I calculate the acceleration. Then I calculate the speed and the x position on the next step. I increase the time, the counter, and return all the results back to Excel. The counter, time, x position, speed. And we continue to run the cycle. Now I will run it in unattended mode without breakpoints. So you can see the results in label mover, or you can see the results in Excel. Again, the plunger hits the initial position